Hi. Good evening, all of you. And we are in our 10th tutorial now. It's almost like we have had a whole day of learning sessions. I'm glad to introduce Professor Vinod and Zinyan and Dehan here today. They'll be walking us through their tutorial on clinical domain and how they had used their techniques to extract information from that. So with that small introduction, I'll just leave it up to them to start the session right now, and then I'll moderate the questions. So folks, as you see, please post your questions in Q&A. I will take the questions up to the speakers. And in case if you need any help, you can just call me out and I'm going to be there right through the session. Thanks so much. Over to you, Vinod and others.
Yeah, thank you very much, Kalapriya. This is really exciting. I have a long history with COMAD, and I'm really glad that I'm able to join today with as a presenter in a tutorial and talk to you about some of the work that my research group is doing. And I'm joined by two of my graduate students, doctoral students, to talk about our work, but also put it in the context of this new domain. Before I get too much into it, are you able to see my screen? And is my audio coming
Yes,
through well? Good,
everything
excellent.
is absolutely perfect.
Perfect, good, great. So as Kalapriya kind of introduced, the title of the talk is Data Science and Natural Language Processing to Extract Information from Clinical Text. I am an associate professor of Learning Health Sciences and School of Information. So my background is in computer science, and I did my master's from IIT Bombay, and then worked at Yahoo for a few years, and then came to US for my doctoral studies, and then continued as a faculty member here. I have now been a faculty member for about 6 years, and Shinyan and Dehan are my most senior PhD students. Shinyan is a PhD candidate in School of Information, as well as Dehan. And we are going to kind of present the work that has happened in the group. So it's really thanks to all of the efforts of the entire group. This is a picture from from late last year. And we got an opportunity to kind of just get together, and wanted to just make sure that I acknowledge all of our work, because not only is this work done by just us primarily, but also in collaboration with all the others in the group and others. And before I go too much into it, this is just a 1.5 hour talk. We can no means cover the entirety of clinical information extraction here, but I want to kind of plug in a couple of online courses that I am part of that expands on this a little bit. Specifically, the one that's launching in March and April of this year on information extraction on health data goes into more detail in some of the things that we'll be talking about. So today we want to kind of talk about this topic in three sections. One is really what is clinical extraction, right? What are the challenges in that? And then look into specifically the clinical entity extraction and detecting adverse events, and through that looking at how text can provide evidence to understand this information and pull out this information from text. So let's start with the first one. The big data in healthcare comes in two different views. So when we talk about big data, the professional view is that you have books or clinical records, which means that when a patient visits the doctor, notes are taken about what the doctor sees and what are the next steps for the treatment, and these are all kind of recorded in medical records. This particular picture is of course about paper records, but recently most of these records are in electronic form, and so we are talking about electronic health records, EHR. And then you have pharmacy information. So when you have medications prescribed to patients, then in most countries, you actually get these prescriptions on the prescription bottle, to kind of say that this particular medication should be taken once a day, one tablet once a day daily, right? But that is also text. So all of these are what text is generated when you interact with health professionals. But that's not all. You also have a consumer-centric view. And that is when people reach out to websites such as WebMD to get information about it. So for example, this WebMD document talks about Erbitux being a treatment for advanced lung cancer. Right? Or they might talk to one another through blogs and other health discussion forums, in this particular case about brain cancer, to talk about their experiences and how they can learn from one another. You have Wikipedia articles, for example, about myocardial infarction, which is heart attack, that is written out by volunteers, right? So it is a community-generated resource, but it is of high quality and maybe one of the top results that come out when people search for myocardial infarction, right? On Google or on other search engines. And then there is tweets. So this one from CDC saying if I mean, this is about Ebola, and I wanted to take something that is not COVID because we have been hearing about COVID all the time. So this one is when somebody with Ebola sneezes on someone else, then the disease may spread, right? So this is CDC as a government agency sharing information about public health through tweets and social media. So when we look at text, you need to kind of infer whether they are giving you the same information. So for example, this first document that we have seen about Erbitux helping treat lung cancer is one of the information from this news article. If you look at another article, this one talks about cetuximab helping advanced lung cancer. You see that this is about advanced lung cancer. So already you know that there are probably two treatments about advanced lung cancer. So at least it's related. But if you look further, it's actually not two. It's actually one, because cetuximab is just a different name for Erbitux. And that is given in the first line of text. Right? And so what that shows us is that you have to disambiguate information that might come in different forms because they may use different words, or they may say the same thing in different ways. And that is the challenge of natural language processing, right? And it happens in clinical domain as well. So this challenge of going from free text coming from books or medical records or websites or discussion forums in social media into a more structured form where you're able to extract this information, link to one another, is the challenge of medical natural language processing. To do that, we need to have the ability to identify entities, to extract attributes. So lung cancer was advanced, right? So that's an attribute to lung cancer. Or determine relationships and assertions, and then link them to other resources and get an understanding of, is it a high quality extraction or not. So we are focusing really only on one aspect of that in this talk, and that is on named entity extraction. Now, I deliberately called it NEE and not NER. We all kind of are probably aware of named entity recognition because I wanted to kind of highlight the challenges of not only identifying it in text, but also pulling it out and then linking it to other things. And that's why it's more of an information extraction challenge, right? So from this document, the named entities here would be Erbitux itself, because that is a treatment, lung cancer, because that is a disease, but there are a lot of other things too, right? So for example, who's the author of this document? When was this published? So this is really from about 12 years old now, right? And other information about this. So, for example, where was it published from? And sometimes these contextual information might also be equally important to identify and give more context, more meaning to this extraction. Named entity extraction is a domain-dependent task. So although it is a named entity recognition task, right? Although it is a named entity that you're identifying, traditional models that learn about person, organization, location might not be sufficient for a particular domain. And clinical domain is just one of them, right? But it could be other domains like legal domain, where you have something like Kirkland and Ellis LLP. There are two names. Yes, Kirkland and Ellis are two names, but this context of Kirkland and Ellis LLP is actually one name, one legal firm, right? And same thing with Skadden and so on. So person names can group together to form a legal firm name, right? When you talk about finance and you have something like Qantas Airlines or QAN.AX are all meaningful strings in financial domain, right? And it's important to get that symbol right and so on. That full stop here is not end of a sentence, but that it actually is an abbreviation where the full stop and something comes after has to be put together. Similarly, in medicine, there are a lot of named entities. So this is an example of a list of protected health information where you have names and dates and addresses and zip codes and phone numbers. So these are all personally identifiable information. That's why they are protected, right? And then you have other things like license numbers and biometric information and IP addresses that appear to be not directly relevant to what we have seen usually in other domains, but they are equally identifiable. The other challenge with entities are something like in pharmacy, 2 puffs orally Q4HRS X90 DYSVs is a valid shortened form of medical prescription. What this is saying is you need it, that the prescription is to take 2 puffs by mouth orally every 4 hours for 90 days for wheezing, right? So it's actually encapsulates 7 different forms, 7 different kind of entities: dosage, form, the route, that is by mouth, frequency, duration, the reason for it, and any other information. For example, the drug name itself would be the 7th one, right? These are all valid. These are all kind of entities of interest in the medical domain. So the before we go into really how do you extract that, I want to kind of highlight the need for annotated datasets. These are the datasets that will help us train these models in a machine learning format, and then also evaluate whether they are whether the models that we have trained are actually of high quality. So annotated datasets are critical for supervised learning, and I'm sure you would have heard about this before, so I don't want to talk about it too much here. But it also I want to highlight that these define the class of interest. As we have seen, the medical domain has lots of entities. Are we talking about personally identifiable information, or are we talking about medication extraction components? That is a task that is defined by these datasets, right? Because they define what are the classes of interest. And then kind of how do you build it, how much data do we have, is how effort intensive it is, kind of defines how much data is available for the training purposes. So I want to kind of leave this one with kind of really knowing whether that data is good enough or not, this is sufficient or not, right? So let's start with one such task, and that is to identify medication entities. So in this particular component, if you look at medication entities in clinical notes, and we'll talk about the data set in a second, there were about 84,000 medication entities, right, coming from these different classes: drug name, strength, form, dosage, duration, route, frequency, reason, and then adverse events. Adverse events are when somebody takes medication, there are side effects. So you would the current term for side effects is like really adverse events, because they are non-expected events coming out of drug use. And by drug, I mean medication use. It's common to say instead of medication, calling it drugs. I'm not talking about drugs of abuse. I'm talking about prescription drugs. Okay. So from this data set, that is the N2C2 data set, this is the distribution of the entities, right? So you have drug names that are most common, because almost every sentence in that data set has a drug name, right? But there are the strength and form is not occurring every time. We don't necessarily say what is the strength of this medication in every occurrence of that medication. And more so with adverse events and duration are much rarer classes. So there is a skewed distribution among these class labels. Another example focusing on adverse events from social media is in a data set of about 25,600 tweets that was released as part of this SMM for Edge social media mining for health data set in 2020. You see again that the non-adverse event labels are about 91% of the data set, and only 9% of the data is about adverse events, right? So again, there's a very skewed distribution, 90 to 10%. So let's kind of quickly go through these two data sets, because this will be what we'll be talking about in more detail in the rest of the hour, right? So the data set on N2C2 2018 is has these 7 different kind of categories. Some of them are rare. Duration and adverse events are rare ones, and drug is the largest class. And you have seen this example of the 2 puffs orally, Q for HRS, X 90 days for V's, right? And note that when I showed it earlier, I split the Q for HRS into 3 tokens, but it typically comes as 1 token, and that 1 token is about frequency, but it has 3 words in it. Q means every, for, and then hours. And then the other example is patient developed rash around arms and started antibiotics. So rash around arms will be your adverse event. The second data set that we will be referring to is the social media mining for health data set, where there are 25,600 labeled tweets, of which 2,300 were adverse event tweets, and about 23,000 were non-adverse event tweets. That is that 10%, 90% split. Right? Examples of adverse event tweets are, "This night is no sleep is brought to you by one." So as you can see, there is a lot of kind of irony and kind of colloquial way of speaking. Right? Metformin gives me bad tummy, but I am on it. Right? Where you're kind of saying that metformin, that medication, is actually giving upset stomach, and instead of saying upset stomach, they're calling it bad tummy. Right? So that's an example of adverse event tweets. Okay, so now with this context, kind of let us look at the next component, which is kind of really going into clinical entity extraction. And I hand it over to Shinyan to kind of take it from here. Shinyan, do you want me to go through some of these too?
Sorry, I was muted. Yeah, I think you can keep going through.
Okay.
Yeah.
That's fine. So let me go back and share my screen. Give me 1 minute. Are you still seeing the task identify various attributes from clinical text? Yep. Okay, good. Thank you for confirming. So let's kind of look at how do you build these clinical extraction tasks, right? So the goal is to use the narrative medical text to identify patients who meet the selection criteria for clinical trials. So this is a classification task. So if you can think about this, you identify whether the patient meets, does not meet, or possibly meets certain criteria. Okay, so it's a 3-way classification task. It's a straightforward classification task, but you need to identify specific attributes and then give the status for that. So it's not a document classification task. It's actually attribute extraction and status identification task, right? Hence, it's an information extraction challenge. Okay, so the context that we are talking about here are substance abuse, so drug abuse or alcohol abuse, numeric values, for example, what is the creatinine level that was talked about in the document, and then what are the complications? For example, are there major diabetes-related complications that have been mentioned in the text? What is the medication history in terms of dietary supplements and aspirin that's being used, and then whether the patients are able to make decisions. So I kind of wanted to group these to show that there can be different kinds of attributes that you may want to pull from clinical text. Right? So just like the example that we showed earlier, this is a skewed skewed distribution in the data set. So for example, the overall training data has 202 documents and the test data has 86 documents. So in a way, that is split into, let's say, about 60-40, right? But if you look at individual criteria, the distribution over positive class and the negative class is not balanced. So the abdominal surgeries or not, an advanced coronary artery disease is basically about so 77 to 125 is still about the 30-70 range, right? 40-60 range. But there are examples like alcohol abuse, where only 7 positive instances were mentioned and about 195 negative instances were mentioned. So that is really a 5% to 95% kind of a distribution, right? Same thing with drug abuse, where only about 12 cases were positive. And the worst case in this data set was that there was this attribute ketoacidosis, where really none of the instances, positive instances, were there in the training data set. But we knew that that was something that had to be pulled up. So what do you do when you have that skewed of a distribution? You want to kind of analyze each of these rare classes, these minority classes, really closely, right? So you need to learn from each instance, because that is representative of all the negative class that is there, and you need to be able to distinguish it even when only 5% of your data set is of that particular class. The way kind of we approach this in the NLP challenge here is to kind of look at the rare class carefully in the training data set and generalize from that rare class. What does that represent? What that one instance represent? That can we learn from it and generalize from it as much as you can, right? And what can you deduce about possible positive instances, even if we have very few instances in our training data? So this is kind of, I want to kind of highlight that task, that challenge, as how do you build this clinical natural language processing pipeline. The main goal to kind of highlight that so early in this talk is that, yes, we will talk about deep learning models and machine learning models going forward, but those are not necessarily the only solution when we try to build something. And those are always a part of the solution, because you need to build that entire pipeline to understand the context that will help the machine learning models and deep learning models later. But sometimes you can do some easy things early on and take it out of the decision making, so that the machine learning models can focus on harder cases and the cases that it can learn from much easily, right? So things that can be done well outside, let's just do it outside. So the first step in that pipeline is to pre-process data. So how do you split documents into sentences, tokens? Should you split Q4 HRS and keep it as one, or split it into 3 tokens? That is a decision that happens much earlier than when machine learning models need to come in, right? And then you can do some certain domain-specific pre-processing, and that's what I meant by this Q4HRS1, where you may want to identify that Q separate and that HRS separate, because then you can use the same logic to say Q3DYS would be every 3 days, right? So you can make meaning out of those tokens if you actually split them into smaller components. So you can identify sections within clinical records the same way. For example, family history is different from the disease history, right? If you're talking about the parent having some disease, that doesn't mean that the patient has the same disease, but it might be important information, right? Then you can split the records based on date for temporal analysis, and then you go into the content analysis. So a lot of pre-processing actually might be important, so that the follow-up stages are performing better. So how do you identify templated elements from text? So dates, phone numbers, email addresses. The most efficient way of doing that is through regular expressions, right? Because they follow a particular style, and so regular expressions are the best way to kind of handle that. What about if the information is there in key value pairs? So for example, if it's a table, or if it says a particular title and then a colon and then a value. So for example, blood pressure, colon, 120/80. You know that that is a key value pair, and your information that 120/80 is the value of interest for blood pressure, right? So that would be, again, a very simple regular expression based approach to kind of pull out that information. HbA1c 6.7%, normal below 6, pediatric 6 to 6.5. You're kind of giving the ranges here, and now you can use that structure, a textual structure, to kind of pull out the information that in this particular patient, the HbA1c value is 6.7. And then because you know from the ranges that 6.7 means that they are diabetic, you can infer that this patient is diabetic. The next task is knowledge acquisition task, where you can pull out this information, the clinical information, to inform the machine to recognize these as specific instances of the domain in the clinical domain. So all classes need some sort of knowledge, right? And this can come from lists. So for example, when you're talking about alcohol abuse or drug abuse, remember these were rare classes, right? But drug abuse would be an example, would be what kind of drugs are abused. So if you want to kind of say something like marijuana, or you have other substances. So for example, if it is a particular medication like Vicodin that people abuse, then those would be the kind of list of drugs that you would want to include, right? Similarly with alcohol, different names of alcoholic drinks, beer, wine, vodka, would not be something that the machine would know unless we provide them in form of lists. So lists of substances of abuse like alcohol, ethanol. Modifiers like abuse, addiction, binge drinking are all kind of adding context to it. And then you have other things about health conditions associated with abuse, like insobriety and so on, right? So those are keywords that might be useful for making the decision of whether there's alcohol abuse or drug abuse. And then other condition like abdominal surgeries, clearly you need to know a list of all surgeries that happen in the abdomen. Heart surgery is not an abdominal surgery, right? But but an appendicitis is an abdominal surgery. So that is what we would need to know, and that the best way to get it is through lists. So what are the sources to get that information? You can have domain dictionaries like gazettes, or medication or medical ontologies, like a meta-thesaurus that is provided in US through the UMLS through NIH, but you have other international resources like SNOMED. The Systematic Nomenclature of Clinical Trials is a data set that's available internationally, and that's a medical ontology that could be used. And then we can use human experts, our domain experts, to kind of give us more information. Okay, so the reason I kind of wanted to highlight this is really it's a hybrid bag of approaches. You can have contextual data where you can look at linguistic patterns through regular expressions and keywords through lists to kind of create some sort of initial models, and then use these ontologies to infer some templated text that you can pull out right away. So creatinine value or HbA1c value are things that can very well be identified using regular expressions, and probably that's the best way to do it. And we don't then necessarily have to train a machine learning model to do the same thing. But then you can use traditional machine learning models to kind of identify other more complex data where you have more data and you can learn from it, and then eventually lead to kind of deep neural network based models to do. Okay, so for example, names of people, you cannot really have an exhaustive list of all names, and so then you would want to kind of include neural network models to do that, right? Or adverse events, because there are so many adverse events and they can be written in so many different forms in free text that a deep neural network model seems to be the right way to do it. Finally, before we talk about these machine learning models in more detail, let me kind of quickly go through the evaluation. The model that I kind of showed that used these regular expressions and keyword-based models and minimal machine learning-based models actually ended up performing the best system on this task. So our micro-averaged F1. So F1 is a harmonic mean between precision and recall. Or if you are aware of clinical domain, then it's the harmonic mean of a positive predictive value and sensitivity, right? And higher numbers are better. 1 is the best, and our micro-averaged F1 was 0.911. And our AUC was 0.9103, and this was the ended up performing, and this was the best system. So just simple approaches, as long as they are developed in a pipeline in a systematic way, can still perform very well on this domain, right? And ended up kind of leading to this JMIA publication. Okay, so to summarize, this schematic of clinical information extraction system is that you have this data that you need to do significant text processing on, identify sections, identify which sections are relevant and which are not, and then using some rule-based approaches that doesn't necessarily need supervised learning. You can identify rules and patterns and still get output on most of the things. And then when needed, you can use the training data in a supervised learning framework to then identify the features and then run traditional machine learning models, or use a deep neural network models that doesn't necessarily need you to identify features explicitly. So in the second part of the talk, we're going to go into more detail about the clinical information extraction challenge and talk about this in more detail in the context of medication entities. Over to you, Shinian.
Thank you, Vinod. Right, let me share my screen. Just give me a second.
While Shinian is kind of pulling it up, if there are any specific questions now, this might be a good time to kind of take a little bit of a pause as we are 1/3 way into our tutorial.
Vinod, I think there was one question, but I think it disappeared somehow. I think there was one question asking what it means by the positive case in the alcohol use in the data set that you introduced earlier about the attribution.
Yeah, thank you very much for that question and for forwarding it to me. So, the positive case would be someone who who has risky alcohol behavior, such as alcohol abuse, right? So, somebody who is binge drinking or drinking much more than what is prescribed as social drinking would be, or somebody who has complications related to alcohol use, right? Including something like DUI, right? Driving under the influence of alcohol would be considered as someone who has risky alcohol use behavior, and that would be considered as someone as in this definition as alcohol abuse. And same thing with drug abuse. So social drinking or drinking under the limits or within control is not considered abuse. We'll talk about it in more detail if you wanted, if the person who asked the question had other follow-up questions. But Shinian, you can continue.
Sure, yeah, thanks. Hope everyone can.
Just one. I think there's one more question. Would you prefer to take it now, or you would like to take it later?
Um, um, Okay, well,
Yeah.
because this is about regular expressions, maybe I can do it quickly. That's okay, Shinian. So how would regular expressions be discovered automatically? Isn't it a manual step that grows proportionally and not just the number of entities? Yes. So thanks for the question, Debayan. Identifying regular expressions automatically is very difficult. What I meant by that in this context is that sometimes that you need to identify regular expressions even to do your machine learning model well. So sometimes identifying them to kind of cover the largest chunk of a particular attribute might still be useful for a follow-up task, right? So that is just like the typical regular expression construction. It is a significantly manual and labor-intensive task and does not have complete coverage, right? It is not because the more cases you find, the more kind of tuning and subtuning you need to do, and that remains a challenge. But sometimes there are not too many variations, and identifying regular expressions is indeed the best right way to do it, and that's what I was trying to refer to there. I see, Sudish, your question, but let's move on with Shinian's component. But I will answer your question in the next question and answer session.
Sure. Okay, so here I'm going to introduce some of the most widely used methods for named entity extraction and also the approach that's developed in our group. Over the past few years, the methods that we use to find entities from clinical text data have traveled from rule-based methods to machine learning-based methods. And now, as you all know, since neural networks has been giving outstanding performance across various tasks, it has become dominant in this task as well. With the rule-based methods, we really need to manually define a set of rules that are associated with the entities that we want to find. For example, on the right, we have this phrase, right, that develop the rashes to a medication. And the special token medication here could be any actual medication name. And if we have such a rule and we can use it to find adverse drug events like rashes. However, it's pretty common that multiple rules might match the same tokens or phrases, and this is almost impossible to manually define the priorities of all the rules when the overlap happens, right? So this is where the machine learning methods come in. when with the machine learning methods, we still have to define a set of rules or features and feed them to the model, and then the model will try to automatically learn towards a particular training objective by finding the optimal weights of those features. Here, I'm going to give a very simple example using what's called conditional random fields, or CRF. And this is a very powerful model that's developed for sequential labeling problems. And for extracting entities from text is a perfect task for this method. Essentially, what happens with this method is that suppose we have this sentence, edible caused stomach and intestine ulcers, and we want to find the medications and the adverse drug events that might be mentioned in the text. We first define a set of features, and for each token, we first need to define the set of features for each token, right? And then we need to we will have this feature matrix, and we send the feature matrix to the model. And if we are training a model, it will try to maximize the likelihood of the sequence of the label sequence given the text, by finding the weights. They do this by finding the weights of each feature, and also try to figure out how likely the labels would transit among each other. So if the model is trained, and we are simply trying to apply the model to the text and try to find the labels, get the label predictions. In this case, for each token, it will just integrate the feature weights and the label transition values to find the best label sequence. With the deep learning methods that has been very popular in these years, instead of using handcrafted features, we use word embeddings. Well, word embedding is a vector representation of a token, and it's usually pre-trained from a large model on large corpus. Here, I will just talk about a very powerful deep learning architecture for entity extraction task, which is a recurrent neural net with CRF model, CRF layer, sorry. And using the same task example here, we first acquire the embedding for each token, and then the embeddings will be the input for the following RN units. So each RN unit here will integrate the embedding that's sent to it, as well as the output of the neighbor RN unit. So we call the output of each RNN unit as the hidden states. So we can think of it as the some sort of contextual semantic information of the current token. So given the entire sentence. So this is basically saying what this specific token means given the current context. And then the RNN output will be transformed into some sort of log likelihoods. And then we use the CRF layer to make the final decision. And this is how the RNN with the CRF layer works. Ideally, the RNN model here could be replaced with any other neural nets that can be served, as long as they can be used as an encoder. So as of now, I think most of you should know that transformer-based models are very popular and they are very powerful. So all these models are very good options too. So here I would like to introduce one of the methods that was developed in our group earlier. We noticed that the current methods have been treating all the tokens equally, and but in the real clinical text, such as clinical notes, the entities are usually very sparse, right? So compared to the non-entity tokens, and we can call the non-entity tokens here as background tokens. We noticed that many background tokens are in our earlier baseline experiments, we found that many background tokens are misclassified as entities. So what do? We hypothesized that if the model could be indicated by the presence of the entities in advance, and then the model would be able to make more precise decision on classifying those entity tokens. So this means that what we want the model to do is to first differentiate the entity tokens versus background tokens, and then perform the classification on only the entity tokens. So now I'm going to use this example to show how the model would perform on the token in testing specifically. So first we will have the embedding for each token. And now I'm only using the three, because of the limits of the space here, I just use the three tokens. So first we will have embeddings for each token, right? And then we can use the RNN model to encode the sequence and generate a hidden state for each token. And here, and the hidden state here could be HT minus 1 and HT plus 1. And HT is the hidden state for the token in testing. So next, we will combine the hidden state HT with its two neighbors. And the two neighbors are the hidden states of the left and the right token. And after that, we can use an entity indicator to decide if the token in testing is an entity token. Okay. The entity here will use a what's called convolution operator to infuse the information in the three combined hidden states. And as the output, the indicator will inform the model how likely the current token in testing carries any sort of entity information. And we do this by scaling the hidden state HT with the probability P. This will give us another state representation. We call it a GT. And at the same time, besides GT, we can have another representation, and we can call it a G prime T. So the only difference here is that we use the 1 minus P to scale the hidden state HT. So we want the G prime T, compared to the GT, we want the G prime T to carry non-entity information. So next step is to gather all the GTs on the left and use the CRF layer to make the predictions. So this is very similar to the standard way of using RNN and the CRF layer. And this CRF layer here will be the main predictors that we use to generate the final label sequence predictions. And similarly, for all the G prime T's on the right, we can also have a sequence of predicted labels with the same CRF predictor. But to differentiate it from the main prediction on the left, I will just call it as a auxiliary predictor when the input is G prime T instead of GT. The auxiliary predictor here is not used at all when we want to when we try to make the final predictions. So we only include it in the training process to help make the model perform better. So this is basically the workflow of this model architecture, and we call it focused entity recognition. Now the problem is how to train the model. We have three training objectives for the model. The first one is designed for the entity indicator. We formulate the indicator as a binary classifier to classify for each token as if it is an entity token or a background token. And while the indicator is being trained, we will also add some noise to the indicator and to force the model to further force the model to keep the entity tokens far away from the background tokens. And the second training objective is for the main predictor. So the main predictor is trained by minimizing a negative log likelihood, which is exactly the same as how we train the standard RNN CRF model that I just talked about earlier. So I'll just skip the details for now. But for the auxiliary predictor, this is a little bit tricky because the expectation here for the auxiliary predictor is that everything coming out of it, if we send them to the CRF layer, we are hoping that all the predictions should be the background tokens. So this means that the target label sequence here should be all the background tokens instead of any of the actual tokens that we see in our training data. So this is saying that we are requiring the model to not only make correct predictions given the indication, but also that when the indicator thinks a token is a background token, the auxiliary predictor is there to make sure that this is true. And if this is not true, there will be a penalty to be added to the model during the training. So here I want to, just in case that you are interested to see that, I want to briefly talk about how the model could be implemented. This is a simplified implementation using Pytorch. And first of all, we can create this entity indicator. So this input here is X. X could be a sequence of hidden states. If we're linking this back to our previous slides, the X here could be t minus 1, ht, and ht plus 1. Then we go, once we have the X here, we have the input ready, and we would go through some of the layers in there and a Gumbel softmax to generate output, which are the probability P, and some logis values that we will use them to train the entity indicator later. And the Gumbel softmax here, can think of it as a mechanism of adding some noise to the indicator, so that it will disturb the model and while forcing the model to learn a better classification between the entity tokens versus the background tokens. And then we can take a look at the main model class folder here, which is pretty straightforward. So we can go through the RNN encoder to get the hidden states, and then we use the entity indicator to get the entity probabilities, and then we can generate the focused representations. So the CRF module will be called later during the training. So I'm just so that part is not included in the part of the class implementation here. So this is a quick overview of how to implement this model architecture. If you are interested to see, as you can see, it's pretty compact and pretty straightforward. Hopefully that's helpful. And now also I want to talk about the evaluation. So we evaluated our model on the in-situ dataset that Vino just mentioned, just introduced earlier. And for the classes with the rare examples, like duration, reason, and ADE, adverse drug events, we improved the performance mainly by having better precisions. This is because the indicator can reasonably identify entity tokens and rule out more background tokens, as we were hypothesizing. So as Vino introduced earlier, the number of training examples for these 3 entity types is very low. So even if we have a significant improvement for these 3 classes, the overall performance improvement is still in a relatively small range. This is also one of the challenge in clinical domain. So we encounter this situation very often because having good and large annotated data set in clinical text is always expensive and sometimes just impractical to do that. So most of the data sets are highly skewed. So there are still a lot of work to be done in this field and how to perform better on those rare classes. Here are some error analysis to showcase some of the challenges that we identified. The first one is what I just mentioned, right? Rare classes need more attention. We need to really pay extra attention to how to address the low performance on the rare classes. And the second issue is the out-of-domain vocabulary. So when we use the pre-training embeddings, it's very likely to have many unseen tokens due to the various reasons here, such as typos, because the clinical notes are written by doctors, right? So it's normal to have typos. And also, it might be just the case that the words are not in the training data, so the language models may the word when we train the word embeddings, the model may never seen it before. And for now, this issue could be alleviated by using more advanced contextual embeddings from language models like Elmo or BERT that are trained in domain with clinical data. Those can help improve the performance a lot, right? And also help addressing all these issues. And the third one is actually the most challenging one because solving it really requires the domain knowledge that is just not included in the text data. So for example, the token hypotensive here belongs to different classes, but with very similar context. It really requires domain knowledge or domain experts to decide which one this one hypotensive belongs to. So therefore, how to incorporate, this brings another very important topic, how to incorporate domain experts' knowledge to the model is crucial in clinical domain. So the next steps for the phono model here, we're going to test out different embeddings and encoder architectures. And we are, meanwhile, we're also looking out for ideas to combine the models with human knowledge to make sure the model's output is better and also the model output predictions are robust. And also we're also looking for ways to improve the interpretability of the model output, because these are another important aspect in clinical domain when we use the machine learning models. So now I think I'll hand it over to Dehan, who will talk about some of our group efforts in how to utilize domain knowledge to improve model performance and even interpretability. Dehan, you want to?
So while Dehan, you can bring it up, Shinin, there are a couple of questions that I think you could handle at this point. One is, what are the typical features used for conditioned random fields in the deep neural network model? So when you have this RNN plus CRF combinations.
Yeah, so wait, so the CRF here, you mean the CRF layer in the deep learning models or the
Correct.
CRF model? Okay.
No, that's what they were meaning, yeah.
Okay, so in that case, usually, the most popular way of when we use machine learning when we use deep learning models, I think the importance of having importance of manually designed features are getting overlooked gradually. So because the embeddings that we have for each token are basically trained from large corpus, and when we train the large corpus from the in domain, that will already give us a lot of semantic information about each token. And if we're using other like language models such as BERT or Elmo, which basically means that all the embeddings of the tokens that we get from the context will be depending on the context. So that's already good enough for us to have a very good performance. But I think there are also people try experimenting different ideas of how to combine the human manually designed features and just try to concatenate them with the embeddings and try to send them. And sometimes that will also help to further improve the performance. But I think those are, in that case, if we really want to try this way, just by simply concatenating the word embeddings and the manually crafted features. So in that case, I think one of the things that I would recommend to do before we actually do this is try to figure out what kind of information is the embedding missing. And in that case, we can design more better features specifically to for the model to be to benefit from. So that's what I guess that's my my point on this one. Does that answer your question?
I think that it covers the main question that was asked. There's another question on what is the advantage that we get using the convolution layer. So why was that used?
What is the advantage of using the convolutional layer?
Yes.
Right. So convolutional layer basically serves as a infusion module because if you remember, I don't have the slide here, but while I was talking about it, I basically trying to say that when we try to decide whether or not a token is a entity or not, we first combine the hidden states of the token and the hidden states of the token's neighbors, and then we use the convolutional layer to infuse whatever the information that we have from the combination. So this is basically allow the model to infuse all the information from the left context and right context and the token itself, and uh, to to further help the indicator to make the final decision. I think that's basically the point of it. But if you have any, essentially you don't necessarily have to use the convolutional layer. In that case, if you have, like, let's say, just simply put, if you want to just use a linear layer, that's also fine. It's just in our experiments we try different mechanisms, and the convolutional layers works fairly good in that case.
And I think we can take probably one more question here, and that was it's a longer question, but I think it's relevant to talk about in this context. And that is, it's expected that these models are going to be memory intensive and will take a lot of runtime. And so one of the questions that is asked is a concern whether these high-end models actually perform improvement sufficiently, or is it only a slight improvement? And if so, then why would you want to do it?
Oh yeah, I think that's a good question. So I think yeah, that's a very good question. I think as you can see, I think you are perfectly correct, perfectly right about this one. For example, when we are trying to we are always trying to develop the better models, and when we have a better model, sometimes it's just frustrating to see that, okay, the improvement might be marginal compared to the second best. I think that makes sense. But I think what our focus is actually not trying to have the best model right there. The idea of having this the Foner model for me was that I was basically trying to figure out why the baseline models were missing out so much on the rare classes. That's our starting point. We're trying to find if there is any way for the model to be able to perform better on the rare classes, because those are the harder classes. And that's the starting point. And I absolutely agree with you. There's still a long way to go. As you can see, the performance on the ADE there is only like around 50 or 60. That's not good enough at all. And I completely agree with you. But this is also one of the challenge with machine learning in clinical domain, especially for clinical NLP, because it simply requires tons of domain experts, and by looking only at the clinical text that does not express any of those domain experts. So I think this is one of the next steps that we're going to take to try to allow the expert to input their domain knowledge in their mind, how to structure that and frame that into the structured way format, and then put that into the model so that the model can utilize whatever the information that the expert has.
Thanks, Jinian. I think we are probably ready for Dehan, but I think if you can answer this in like a couple of sentences, because I think that's what we would need. The question is really about replacing recurrent neural network models with GNNs, and is it possible to use GNN in this scenario?
GNN as in a graph neural network?
Yep. That's what I understand.
Okay. I actually I just had a paper published last year about using GNN to try to augment rules for weakly supervised named entity recognition system. So essentially, the idea is that we're trying to we always have I'll try to finish this in a couple of sentences. The basic idea is that we have like millions of the rule candidates that we can automatically define, but we don't know any of them. We don't know which of them are good enough for us to get our label to annotate data. So in that case, we only need a very few seed rules that are good enough for us. So these seeding rules could be defined by us, and they won't take much time. So in that case, we basically figure out the idea about how to propagate from our seeding rules to larger groups, so that when we propagate, we can use the propagated rules and combine them with our setting rules, and now we have a larger group of rules, and so that we can use that to label more data and try to create a weakly labeled data set, and so that deep learning models could be very useful there.
Thanks, Chinian. So, Rachit, I see your question as well, but we will take it in the third component of it. So, Dehan, why don't you get started now?
Okay, sure. Are you able to hear me well? Okay. So we'll continue discussing some of our work that's specifically to detect adverse events from text data. So earlier in this presentation, we kind of shared this data set in Twitter, and just to give you a little bit of a background in social media data in general in health and the medical NLP research. A lot of health researchers are trying to incorporate these social media data to understand health-related activities from online users too. So in our lab, we do a lot of couple of projects that's based on Twitter or social media data set, and one of them is this data, this work where we try to identify whether there's a mention of adverse drug event in tweets. So I'm not going to go over this tweet example, but the goal for this work was to build a machine learning model to detect these ADE tweets in tweets. So for this CLAPA model we built, the main idea was to we wanted to enhance. Sorry, I hit myself. We wanted to enhance the structure. Sorry, the vector representation of the medical concept. In this case, it was drug mentions like Vyvanse, metformin, Ventolin, and Tamiflu. So we wanted to enhance this vector representation by using this collocation embedding technique we developed. So I'm going to give you an example what this means. So in standard neural network structure, we have this following. At the bottom, we have an input of tweet. And there's a word embedding where we convert this token into a word in this vector representation, and we just feed them into a standard neural net. Now, it could be the LSTM or RNN, others. But we developed this collocation embedding by using this idea of neighbor words around these drug mentions in the data set. And we combine those neighbor words embeddings to compute this the collocation embedding for the drug mentions, to hoping that it enhances this vector representation of the drug mentions, the medical concept. So how we implement this in code is the first part is pretty straightforward. When we initialize a model, because this is an LSTM-based model, we just initialize this LSTM. But the interesting part that comes on the training part. So I'm going to go over these lines of code first, and then kind of more explain how we compute this collocation embeddings. So first, we get this collocation embedding in the input text, and once we get this collocation embedding, we use this concatenation of the word embeddings and collocation embeddings together as the final input for neural networks. So after that, this gets fed into the neural networks, into LSTM, and followed by the self-attention layer. So here we can see it outputs, LSTM outputs the final hidden states, and also there's a self-attention layer which outputs its pulled states as well. So given that, our final representation is concatenation of those pulled states and final hidden states from the attention layer and LSTM layers. But also we have this aggregate representation of medical concept from the collocation embeddings. So this is kind of our overall brief structure about our CLAPA model. And a little bit more about this collocation embedding at the bottom of this diagram is, so this takes, we need 3 different variables. One is called medical entity 1 hot. and neighbor embeds, and 15. We can go over this function, sorry. So we have 3 variables, medical entity 1 hot, neighbor embeddings, and the 15 was the number of neighbor size. So how many neighbor words we want. So the first variable, the 1 hot, it means, so we wanted to indicate where in this text it contains the drug mentions, the medical concept. So for this example, our tweet example, the drug name was mentioned at the very last word. So all the first words is going to be contain 0, but the last word will be a 1. So to indicate, hey, this is the drug mentions in this text. And for the neighbor embeddings, you can think about it as a matrix that contains the neighbor word embeddings. So our example, it was something like this. And for Vivens, we have those neighbor words that was used around this around the Vivens. So using these neighbor words, we compute the collocation embeddings. So we get these attention scores of those words, and then we just sum all those word embeddings together and kind of reformat into this consistent format of word embedding dimensions, so that we can kind of properly fit into the LSTM model. So that's this is it was a very simple technique, but the result was pretty surprising, because we got a lot of better score on F1, but also on the recall side, we got much higher on the recall. So this means that by enhancing this vector representation of drug mentions, this model, Klappa model, was able to identify more positive cases. The positive cases here was more AD tweets, AD-related tweets in this case. So that was kind of our conclusion. And in the following year, we extended this Klappa model into a BA-Klappa model. So this stands for BERT-assisted Klappa. So again, this Klappa model takes this input of tweet and looks at this drug mentions focus. This focuses on the drug mentions. So you can think about it as a concept-focused representation from Klappa model. But BERT, on the other hand, is it's very powerful model in recent years. And if you are into like NLP, you've probably heard about this model's name, like BERT, and a lot of people are using it. And the why it's really powerful is because this so the key difference between the LSTM or RNN model versus BERT model is BERT model, because LSTM, in general, neural network model takes one word at a time and try to understand and learn from it, from the sequence. But on the other hand, BERT learns this, takes the full sequence, the full text at one time and learns from it. So it kind of provides this, it's well known for providing contextual information about this entire sequence. So that's kind of the key difference between BERT and the other model. So we thought that why don't we combine this concept-focused representation, and the other is a more of context-focused representation, and combine those representations to have a better prediction. And the implementation part was it's straightforward relatively. So we have a Klappa model on the left and the BA-Klappa model on the right, and the only difference is we just initialize another pre-trained model. We call it BERT here. And there are many packages, not even a Pytorch, but other packages also have provide this BERT model, so you can simply just initialize models just like an LSTM and other neural networks. In the training part, the changes is here. So instead of use this final representation as a final output, we change it to as a Klappa representation, which was the concept-focused representation, and we just run the same example on the BERT to get the contextual representation. And we just concatenate these two representations, Klapa representation and BERT representation together to have this as a final representation. And so this also happened in the following year. So for the SMM4H 2020, we compared these two models together, and the BACLAPA, the extended version of CLAPA model, performed way better. And also it performed a above average of all evaluated systems during this time. So one of the fundamental steps to make a correct decision in social media data, tweet data set, and even in clinical notes, was to find the relevant contextual evidence. So for CLAPA model, for example, we try to enhance this representation of medical concept. And for BACLAPA, we try to add this more contextual representation into the model. But in clinical notes, on the other hand, the contextual evidence is pretty straightforward and thus easy to identify. So if you look at this example of a clinical note, you can see that there's a past medical history, colon, OSA, patient denies smoking history, patient is not a current smoker, and so on. So once we go through this quickly, we can kind of notice that we can kind of see some like information about this patient. This patient does not have smoking history, is not a current smoker, and there's no chest pain, no palpitations. And also, if you might have noticed, there's also section information that can be very informative to us. So when we look at it, for the first part, we kind of assume that, oh, this is about history. And the second part was, oh, this was about the signs and symptoms. And then we kind of expect what to come. So if this contextual evidence is easy to identify, then instead of feeding, so this is related to the question about the computing using neural networks, although there's high computing power. So instead of feeding this text into neural networks and letting them learn whether or not this patient is a smoker, we can just build simple rules to do it because the contextual evidence is clear here and concise in this case. So I'm going to show you some examples of how we develop rules based on this evidence. So say we wanted to find out this different status about complications or adverse events. So it could be like smoking history or having whether chest pain or rashes. And then we can kind of define rules based on the contextual evidence. So for negative status, we can kind of see that there's a mention of like no chest pain, no skin rash, or no evidence of smoking history, and denies smoking history. And for the next class, or for the next history status, the contextual evidence used can be just history of skin rash, or HX as an abbreviation for history, or H/O as a history of. Also, another example can be like this patient had rash in the past, and they can also kind of be saying that that the status was in the history. And so for resolved class, there can be resolve, kill, and clear. And for improved class, there can be help or well controlled as contextual evidence. And worsened is flare or discomfort. And the ambiguous status is the rest that we were able to identify the keywords, for example, like smoker or the chest pain, but the thing that we couldn't really find other contextual evidence, then we kind of have to deal with just this is an ambiguous status. There's a mention of certain complications or disease, but not any other contextual evidence. It's ambiguous. And also the section information, we can kind of use the information to have more we have more priority, so we can prioritize one section over another. So say we can say like assessment in the information in assessment and plan is more important than information in the history because it's more current ongoing thing. So using this rule, we can kind of develop very simple algorithm. Which you can think about it this as a decision tree where we just check for our rules, and if it falls into that rule, then we labels as the following status. So if it's under the negated status rules, then it is a negated status. And if it's not, then it goes to the next status rules, and then we check for those rules, and so on. So in the end, if we weren't able to identify any rule or contextual evidence in the given text, we kind of leave it as an ambiguous status for the doctors or for us to look at. And also, if needed, we can kind of label some like very small amount of data, like a couple hundreds, to make it as a kind of semi-supervised approach. So we can use this annotated data set to train a machine learning model, but at the same time, we can incorporate our rules that we defined into that model together. We can like try a hybrid approach, or we can incorporate it into the model too. So that's kind of one way. So actually, we've been like using this method as well in our lab. So we want to share that result. So the first work was on EIM status identification. So EIM stands for extraintestinal manifestations in IBD. IBD stands for inflammatory bowel disease. So for those of you who are not familiar with it, it's so IBD is Crohn's disease. It's a disease happening in the gut. And EIM, you can think about it as it's a complication or adverse events that's happening because of IBD, but Crohn's disease, but happening outside of the gut. So it can be affected in an eye or skin or in a bone or joint or something. So we want to identify this EIM status of the patients. So for example, even a note, this rule-based model takes the note and finds where exactly the keywords or the interest, the EIM status, EIM classes is located in the text. So I forgot to mention that we had 8 EIM class, and one of them was psoriasis, and there are like arthritis and so on. So for this example, was on the psoriasis, and given this example note, this model was able to find psoriasis in 2 different sections. One was on the past medical history, and the other one was on the assessment and plan. And the evidence text, so the actual text in the note was this. So the rash has been diagnosed as a psoriasis in the past, which indicates it's a history status. And the second part was on the patient feels her psoriasis is better as well, so it's an improved status. And then because we have this section priority, we vote for the assessment plan text. So we conclude the final label as an improved status rather than the history. And the second example is a medication status identification model. So this model just has a pretty similar pipeline. It looks at where medication is located in the text and finds the evidence text. So in this case, there are 3 different sentences where the medication was mentioned. 2 were in the history section, and 1 was in the assessment plan. And the evidence label was the prior use, history use, and then for the assessment plan one was consider use. And given the information, this model concludes as a prior use. So using this rule-based model is really effective, but it's not really fancy as a when you think about like deep neural network, but it's still like effective. And I want to also emphasize that it's really good for interpretability. So we can kind of you can kind of understand what's going on and how this model made a decision using this evidence text, and where to fix if there is any problem in this model. So that's kind of one takeaway of using this simple approach, but still effective. So yeah, I'm gonna take it over to Vinod, but
Yeah.
if there are any.
Thank you. But Dehan, if it's okay, can you continue sharing your screen?
Oh yeah, sure.
Thank you. So hopefully in the last kind of 75 minutes of kind of our presentation and question answering, you kind of saw the challenges that clinical domain presents, right? We have tried to kind of show you a variety of the challenges and some of the approaches that we have been approaching. And these are not completely, I mean, these are pretty representative of what the community itself is doing. So even though we have kind of highlighted some work that we are most aware of and comfortable with, that is also representative of what the community is engaging, right?
Vinod, you are muted.
Sorry. And Dehan, can you go to the next slide? Yeah, thank you. So we are kind of looking at how named entity extraction is an important task in natural language understanding and how different domains have different needs. And next again. And through the work, we have shown that a clinical information extraction presents this unique opportunity to incorporate domain knowledge, right? We have shown it through examples in alcohol abuse, drug abuse, things like creatinine and HbA1c values. Shinian talked about how to use it for medication extraction when you have really hard classes, and how these deep learning models can improve the performance of otherwise models like SVM that do not perform as well, right? So when the task is relatively straightforward, you don't want to bring a bulldozer. You can do it with simple models. But when it is actually a task where simple approaches don't work, then ability to be able to do that using machine learning models and deep neural network models gives us that extended range to be able to do it. So you can learn from this external data using pre-trained embedding and knowledge sources, but then you can incorporate the domain knowledge into it. So Dehan, if you click one more time, kind of deep neural network presents that approach to be able to do it. Unlike others who work on clinical NLP, probably I think we come from a mindset that it is not necessary to have the best the best kind of most complicated model to be the model that is used for every instance, right? And that's the kind of referring to the question that was asked earlier from Jai Krishna, I believe, where kind of saying, why do we want to use deep neural models? Yes, we don't want to use it every time, but being able to think of this as a set of tools that we want to kind of pull from as and when we need it, I think becomes a important data science approach. And so the highlight that we hopefully have raised through starting from the NLP pipeline, going through deep learning models, but coming back to evidence in what Dehan presented, I think we are hopefully able to communicate that it is actually a pipeline. And looking at what models can be put in place and pulled out and put and replaced gives us the ability to kind of improve the overall performance in a clinical information extraction task, and hopefully through that in a clinical decision making task, right? So the main purpose of this is not just to identify the concepts, but to really use it in a downstream clinical task where you want to use the artificial intelligence models to help explain the most important characteristics, and then use those in the decision making, right? We will leave this slide up as we take up additional questions, so please keep these questions coming. But Kalapre, do you want to kind of I know that you came online, so just wanted to make sure whether you wanted to say something before we take the rest of the questions.
Not anything specific. I just wanted to reiterate that there are a few questions pending on the Q&A session. Yeah.
Yes, yes, absolutely. Let's go with the question that was the oldest that has not been answered, and that is really about from Sudesh on how handling the semantic identification of diseases is important. So cancer can itself be mentioned by sarcoma and other names, right? In fact, different cancers have different names, like lung cancer is a different name and blood cancer is a different name and so on. And this is why the domain knowledge becomes important. So using the resource, using the knowledge resources like you have as a vocabulary of all words would be important, and even the semantic relationship between them, that actually cancer is not one disease, it is actually all these cancers together, right? And then looking at leukemia and lymphoma and all of those names as inherited classes of cancer or different specific classes of instance becomes important. So some things might be most relevant only to lung cancer and some to the cancer in general, and being able to do that in form of a knowledge graph is a critical kind of research work that we are currently focusing on. Another question that I think was left behind was on identifying vocabulary words, and this and Rachit was kind of highlighting that tachycardic is actually both tachyo and then cardiac, and then you can kind of link them together. That's an excellent idea. So what you are kind of saying is usually these are generative words. So you can think about pneumothorax is something where you can use the individual components of the word to identify what it might refer to, right? And that helps increase that range of the domain knowledge that we have into words that we may not have seen in the repository, right? So, for example, ileal connection and jejuno-ileal connection would mean similar, but we know that jejunum and ileum are both parts of intestine, and so these kind of help us identify that the disease is not only in ileum, but it's in this range of jejunum and ileum, even though that particular word might not be there. So, absolutely, I think that is a good idea. The way most of these models work on it is that a lot of neural network models focus on word-based embedding, but more than that, I think sometimes the prefixes or character level embedding appears to help more. So if you are able to identify, split that word into its prefixes and suffixes, that as a whole might actually give more information about that particular context than just a word itself, because the word might be out of vocabulary. So that these models are still happening, and so your idea is completely in line with what that line of work is. Jay Krishna, your next question is really, why can't we use ensemble of much simpler approaches, as the kind of diverse knowledge from weak learners is much better than complex models? You are right. We have used ensemble of different models as well, and so that is where that pipeline comes in play, where you can look at individual classifiers and then combine the models. But I don't want to leave an impression that deep neural networks models are not useful, right? There is because you have asked a couple of questions in that line. So yes, as much as you can with embedded ensemble models, you should use it. In fact, we have used it too. There are certain tasks that are very difficult for simpler models to work with. Support vector machine models are linear models. Linear models have a limitation that they are linear models, right? So the advantages that these new deep neural network models bring in is that connection of kind of skipping terms, looking at that in a more contextual way, and learning from the entire context than only focusing on one word or kind of this linear combination of features. Two, they are so the model is actually a neural model, which means that you have these individual factors that come in that activates the overall scene. If the combination of that, if a non-linear combination of the features are strong enough, that is when the neural network model kind of fires, right? So neural network models brings in this non-linear combination of features. It could be a very simple neural network model. Perceptron is a non-linear model. Actually, Perceptron is a linear model, but you have a two-stage model will be a non-linear model. You can do that as well, the advantages of these new neural network models is to highlight hidden patterns that may not otherwise be available. And that is the main reason why the natural language processing approaches more recently have gone into that realm, because sometimes language is complex and it's not necessarily only defined by a linear combination of features, even though you come up with most extensive features. And that is the main kind of power of it. Do Shinny and Dehan, do you want to kind of add to that discussion? We are just a minute over, and I want to kind of touch upon one more question, but I wanted to give you an opportunity
Yeah.
to contribute.
Yeah, I do have something to add to it. So I guess so overall, what I would like to say is that using which model is very much depending on your task and your purpose. For example, if you are trying to really explain the model, you really need your output to be faithful and trustworthy. So in that case, I guess neural net model might not be the best case, might not be the best choice, although it might give you the very good results. So that's that. And also it really depending on the very challenge level of the text. For example, if we are talking about the really text understanding, that means that we really have to we really need the model to have a very deep understanding and deep semantic information that are extracted from the text. So in that case, neural model is very powerful in this case. But if let's say we're doing the entity extraction, sometimes we've been argued that by doing a very good job in the entity extraction tag, sometimes what we really need to have is just some shallow information, shallow features, which means that we can have like very good patterns. These patterns does not require us to really understand what the words mean, but it's just as long as we can observe those patterns from the text, we can confidently label whatever the matched information as the entity of interest. So that's the one more point that I would like to add.
Thanks, Shinian. And Dehan, while you kind of add your 2 bits to it, can you also take the next question, which is really about the rule-based model uses the 7 different kind of status, while we talked about deep neural net models to kind of use for identifying entities. The question really asks whether we use CRF or other models to handle these features.
Oh, that's a good question. So the second work, which was on the medication status identification, was on basically based on the neural networks, if I'm correct. So that's a semi-supervised approach, supervised approach where we incorporate what actually it was a CNS model. So maybe I need to confirm with it, but it was a BERT-based or which model was it?
Right. So essentially the IBD work, the second work that Dihan showed in the last slide was trying to identify the status of medication use from the clinical notes. Apart from, different from the rule-based method that Dihan was using, I was trying to see, suppose we're able to extract some of the evidence text as our candidates, and so that we can make a document note level or document level decision based on the extracted evidence text from the clinical note. But what I was trying to see is that whether or not if we can already get some medication use information from the evidence text itself. So to find that label information from the text itself, where I was trying to see if we can train a neural network model to see, because neural network model is very good at a sentence classification tasks. So this is how I started, and then I also realized that the challenge. Suppose the doctor is trying to do this job, and the doctor need to annotate a lot of text by his own or her own, right? So that's a very costly to do. So this is where I started exploring how many evidence do we need to train a robust evidence identifier. So that we were using over 2,000 nodes as our entire data population, and we only annotated like 200 evidence sentence, and that already give us a evidence classifier that can classify the that can perform classification on the sentence with over 90% accuracy already. So this is basically saying that if we we just by annotating a very small amount of data, we can achieve a substantial performance compared to the other methods that does not use any of the evidence from the data. So that's the whole takeaway of the work. Yes, I think if really, so it really depends on your your budget, your method, your purpose. You can choose whatever the method, either rule-based methods or machine learning-based methods that can best fit your interest.
So I think the big conclusion there is that as data scientists, we need to be well aware and well versed with different techniques, and not only just that we can use it, but when to use which approach, and kind of use it more kind of in a smart way, where yes, all of these combination ensemble are all valid tools in the quiver, right? But kind of using them in an intelligent way can help us perform and get more from little data that we have, and especially in a domain like clinical domain, where the data, annotated data, is sparse. We are 5 minutes over, and I want to be respectful of everyone's time. And so thank you very much for everyone who attended this. We had about 55 people at one point, and I know that it has been a very long day of tutorials for you also. I really appreciate you engaging with us. Please do reach out to us if you have any follow-up questions, and we'll be more than happy to kind of walk through that and discuss this further with you. Thank you.
Yeah. So, Professor Vinod, I think I just thought I'll take 2 minutes to summarize this. I think this was one of the finest tutorials we had. We can't ask for anything more on a Friday evening because it's like the time when people usually you have to drag them to the desk to make it sit. But I think it was fantastic. I really liked the entire flow of the thing, and there was lots that I think I'm going to take away from this tutorial personally. So that was very nice, and thanks to your team, Dihan and Zinyan, to spend this your morning and our evening. It was a wonderful session, and if there's any further things, once we have some community things like this, we'll pass it on to you. Thank you so much again for this wonderful tutorial for us.
Thank you. All the best.
Yeah, thank you. Bye. Bye. Sorry,
Bye.
1 minute. I just thought I'll take one a snap. If you could just switch on your videos and stop your presentations, we can just take only the pics of us.
Yeah, that's great. So Dehan, if you can, yeah, perfect. Excellent.
Yeah, a nice. All of us say cheese and then we end it. Yeah, thank you so much. It's done.
Thank you. This is a good experience. We really enjoyed it.
Yeah, I really like being part of it, and thank you everyone who has stayed back for the presentation for this long. And I'm sure that the keynote speech is going to be excellent. And so we look forward to having more time kind of engaging with all of you.
Sure. Yeah, and as you said, we had excellent participation. We had like about 55, and in a Friday evening, it was good.
Yeah, excellent.
Yeah,
great.
Thank you so much, and see you all in the other sessions. Bye.
Sure, thank you. Bye.